Now, the last part of Unit 2 is on multiple givens. Multiple givens. And now, yesterday's lecture, hopefully all of you went home and really looked at yesterday's lecture and went through it. Because it's crucial you understand yesterday or today. Okay, so let's look at a typical limiting reactant problem. Basically, if you're given more than two givens, that's one of them limits the production of the product. Okay, so 23.2 grams of ethane are burned, 34 grams of oxygen are consumed. How many grams of water are produced? Okay, so this is the equation down here. So ethane is C2H8. Now, on the test, I will give you the formulas. I'll name the chemicals, but also give you the name. Okay, so ethane is typically in a butane lighter. There's ethane. Ethane comes out of a wall to run your stove and your hot water heater, etc. It's a very common hydrocarbon. Hydrocarbons only have carbon and hydrogen in them. Gasoline, hydrocarbon. Diesel, hydrocarbon. Jet fuel, and there's a lot of hydrocarbons around. And most of that comes from oil. Okay, so we have ethane burning in oxygen environment yields water and carbon dioxide. Okay, so I went ahead and balanced it. Now, one other question keeps coming up regarding the extra credit balancing equation. Bring that in completed, and when you turn your test in and your take-home problem, don't forget, staple it to the back of the test, hand it in for Monday. All right, so let's go over the bicycle problem again we did yesterday. Now, if you remember yesterday, right at the end, I mentioned if you have 10 wheels, and 10 frames, how many bicycles can you make? So remember, there are two wheels. There's a two-wheeler now. It's two wheels per bike. So if we were just looking at 10 wheels, how many bikes would that make? 5. And at only 10 frames, how many bikes would that make? Just frames now, no. 10. Okay, I'm looking at those independently. So we're going to do the same thing, only with chemicals. The two givens are 10 wheels, 10 frames. So we calculate them independently how much product we make. Whatever makes less product, it limits the reaction. So you have to do two calculations to start with. Does everyone understand how we know the wheels limits the number of bikes? So that would be the limiting reactant, would be wheels in this case. All right, so let's look at starting with ethane. Okay, molar mass for ethane is 32 0.10. Okay, and we're looking at water now. So water is going to be on the top. ethane on the bottom. So ethane has to cancel. And ethane's 1, water's 4. Right. Okay, now we need to go from moles of water to grams of water. So water is 18, is it 1801 or 18? Now this will give us grams of water produced. So that's looking at ethane only. Now we're going to look at oxygen only. So the oxygen limits the production of water. So that's the limiting reactant. Okay, so you always have to do as many reactions as you have givens. So we had 2 givens, 2 of these reactions. 3 givens, we have to do 3 of these reactions. Now in your car, when your car burns gasoline, the computer in your car optimizes the oxygen that's coming in from the air. It analyzes the percent oxygen in the air because it varies. If you go up in the mountains, there's less oxygen up there than down here. And it then changes all this stuff. So this limiting reactant for gasoline powered car is controlled totally by the computer. Before computers control cars, that was all done by a radiator. And the problem with the radiator is it's set for one elevation, sea level. So when you go up the mountains, what happens is the car runs very rich. So you lose a lot of power. And that's the real advantage of computer control, is you don't lose any power. So it maintains that stoichiometric ratio. Okay, so we found out via this, oxygen is the limiting reagent. Now, so the oxygen is totally consumed limiting reagent again is consumed 100%, totally used up. The other one, only part of it is used up. So that's the next calculation. How much is that? So what we're going to do is we're going to start with the limiting reagent. Which ethane is used. This will tell us how much ethane is used. Then we're going to subtract that from what we started with. So this calculation tells us how much of the excess given is used up during the reaction. But we started with 23.2. So we have a little over 14 grams left over of the ethane. So these four calculations are done on every single limiting reactant problem. Every single one. Now, frequently they'll ask you for the percent yield. To do the percent yield calculation, you have to know the actual yield. What we just calculated is 19.4 is the theoretical. The actual is what really happened. So we got 5.67 grams. Actual. The, what was it, 19.4. So we had an actual yield of 29%. Okay. So every problem is going to have these parts. Now, if you blow the balancing of the equation, chemical equation, every one of these is going to be wrong, these calculations. Because every single one of them involves the ratio of the coefficients from the balanced equation. So it's really important that you balance the equation properly. And also that's why you do it first. It's because it's needed in all the calculations that come after that. Yeah.
For the actual, or for the equation that we just did to find the actual yield.
Actual yield is given.
Given, sorry, so then our plot, that, whatever the actual divided by the theoretical.
That's the percent yield.
Percent yield, how would you like that? Do you want us to just write like 29%, or do you want us to write 29 times 10 to the second?
Oh, just normal. No, it doesn't matter.
Oh,
And it wouldn't be times 10 to the second, it'd be 2.9 times 10 to the first. Remember,
oh,
the scientific notation is gonna have a number from 1 to 9.
that would be 2.9.
Yeah. Okay, are there any questions about this? Now you can see why I was telling you yesterday that doing the simple one is extremely important, because we did it simple one 3 times here. 3 times. And the last calculation, next to last one where we found the excess, that's a straight subtraction problem. And then the percent yield, you have to be given the actual yield. So it's actual over theoretical times 100. Now, in your lab packet, they always say 100%. That is wrong. 100% is 1. If you multiply by 1 by 100, calculates percent. But you're not multiplying by 100%. Okay, there any questions about this? Okay, let's do another one.
You are, like, if these kind of questions are gonna be on the test, are they gonna come to balance, or do we have to balance them as well?
No, nothing I give you comes pre-balanced unless it's balanced. I mean, you'll see the numbers. Otherwise, there will be nothing there. So assume everything is unbalanced. And this one you're not going to do in class, you're going to do at home. Okay, so this one here is 23.2 liters of ethane at SCP are burned, 34.5 grams of oxygen are consumed. How many molecules of water are produced? And then how much of the non-limiting reactant remains? Actual yield is 5.67 times 10 to the 22nd. And you need to find the percent yield. Okay, so same thing, we need to do 2 calculations right off the bat, to figure out which one is going to be the limiting reactant in this case, or the limiting given. I've already balanced the equation from before. So we're starting with masses in liters. I'll usually say at STP. If I don't say at STP in my class, Chem A, assume it's at STP. Your next class, it will not be at STP. They purposely don't do it at STP, and they force you to use the ideal gas law. Figure out what the volume is. Okay, so that is going to be the ethane. So that's the C2H8, and we're calculating water. Molecules of water. Okay, so we're just going to do the same deal. We need to convert given into moles. It's 22.4 at STP. Liters cancel. Equation, coefficient ratio is 4:1. And then water is 1802 grams per mole. Now, are we calculating grams of water? No, we're not calculating molecules. So instead of 18.2, we're using good old Avogadro's number. Okay, so let me grind this out. Let's see. So that's 2.49 10 to the 24th. Now we're gonna do the same thing, this time with the oxygen. And how many? 3.5. Okay, so the amount of oxygen again limits the reaction. 10 to the 23rd is quite a bit smaller than 10 to the 24th. So the limiting reactant is 100% consumed. And then the excess is partially consumed. So this would be the H2 or the O, and then this would be the methane. So now we need to find out how many molecules of ethane were actually used. So we start with the limiting reactant first. So that'd be the oxygen. The excess is going to be the ethane. And now there's a challenge here. What's the challenge? I want to know how much excess. You subtract molecules from liters. We need to convert one of them to either liters or one of them to molecules. So they're both the same. Does that make sense? The units have to be the same before you can subtract them. Otherwise, apples and oranges. Okay, so let's or we can convert to grams, both of them also. Inches. So let's just go to molecules. Okay, so we're starting with 23.2 liters of ethane. And what we're calculating now is how many molecules we started with. So we can then subtract the molecules we used. Okay, so it's going to be okay, so we started with 624 times 10 to the 23rd molecules. And we used 1.62 times 10 to the 23rd. So whenever you subtract or add scientific notation, you've got to get the exponents the same. In this case, they're already the same, but if they're not the same, you have to make them the same. Because you can't subtract them if the exponents are different. In this case, they're both 10 to the 23rd. So it is 624, 162. This is why it's a take-home problem. Now, next class, it will be not a take-home problem. You have to do these in class. It's really important that you're taking this class first. So you get to know what's going on before they whip through this. And I have a student that just finished my spring Chem A class. She's in 2A right now. And she goes, really helped her. Now, she was an A student also, which helps. Very fastidious. And Erin, you would like this person. He's also OCD.
I remember you telling me about how like, product, like,
Yeah, her stuff is exactly like yours. When she puts her numbers in the calculator, she puts the ones in. That's why I wanted you to meet her. Okay, any questions about this so far? Yeah.
Can the excess be in liters?
Yeah, I should have, I didn't specify. So yeah, either one's fine, or you can convert it everything to grams. I didn't specify. But I did say the actual yield was molecule. So that's why maybe 60-40 molecules over liters. But unless it specifically says whatever, your response to me is, well, why don't you tell us? Okay, so 567 is the actual yield. And the theoretical yield was 6, no, what's the theoretical yield is what? 649. Now, when you're dividing and multiplying, you don't have to make the exponent the same. Only if you're adding or subtracting. So that's 8.7%. And that is a very traditional limiting reactant problem. Now, some teachers will give you 3 givens. And so what you'd end up with is this part up here. This part would be 3 equations instead of 2. But this is the number of givens. 2 givens, 2 equations to find out which is the limiting reactant. Okay, so any questions about this? That's a whole page. 1 problem per page. Yeah,
Are you gonna give us the conversion sheet, right, the conversion factor for the test, or do we have to price?
the only conversions you need to know are molar mass, which comes from the periodic table. I'm giving you a periodic table, and 2 more. 22.4 liters per mole of gas, and Avogadro's number. So I may include those on the test, but you're going to use it enough so you kind of already know them. All those other conversions, we're not using those. Unit 1's, yeah.
Or do we get that number on the test somehow, like? Not about there's no. It's not.
No, the conversion sheet doesn't talk about moles or anything because that's unit 2 stuff. So I can put it on the test. It's not a big deal, but you probably already know it because you've used it enough. If I forget, we'll just write it on your test, okay? I'll put it on the board or something like that. Okay, if there are any more questions, we are done with unit 2. Now, unit 3 is going to be very similar to unit 2 in terms of complexity. Some people think it's more complex, but I think it's about the same. Lots of molar stuff. Now, I'm going to go out on a limb. I was told by the person that is the lead instructor on this class not to teach pH. But I'm going to teach pH this summer, how to calculate it. Not very hard. It's the negative logarithm of the hydrogen ion concentration. And logarithms are simply exponents. Everyone makes them out to be very complicated, but they're just exponents. In fact, that's how slide rules work on logarithms. Did you ever, any of your teachers, your math teachers, bring in the slide rule? I used to always bring in a slide rule and say, who knows what this is? And I get like 4 hands go up. And I say, who knows how to use it? And all the hands go down. Well, it got us to the moon. If you ever watch Apollo 13, the movie, there's a bunch of scenes. There's a sea of engineers in this giant room, and they all have their slide rule. And that could have been our undergraduate program at Davis. Everyone was walking around with so everyone owned at least 2 or 3 slide rules. You can't have enough slide rules. I even had a little bitty one. I used to do my gas mileage on my car. And And they had really cheap ones, made out of plastic, and they also had ivory, made out of ivory. Obviously, the ivory ones cost a lot more, so I always had the plastic ones. They work the same. 3 sig figs, no more than that. Okay, so we're done with the unit. So tomorrow, we're gonna start on solutions. And solutions are, we're gonna do liters again, but they're not gonna be gaseous, they're gonna be liquid liters. Entirely different. Entirely different. For pH? No, we're gonna have a titration lab, which is an acid and base lab, which we're gonna do some calculations using pH. And I'll show you how to calculate it. You're gonna be using the log function on your calculator. So it's really easy to do though. Just go negative log, then whatever concentration is, but then you go the opposite. If I give you pH to convert to actual concentration, let's go the other way. I put the pH in the exponent. So it's 10 to whatever the exponent is.